Afternoon. Sorry to do this to you again, but as you can probably tell by my voice, I'm not feeling terribly well. So I am going to come back on Tuesday and we'll go over some of this material again with you the next couple days, particularly the idea of limits and then what we're going to do with those limits on Tuesday. So on Friday, we looked at the idea of limits. We looked at the ideas for relatively simple functions, something like a polynomial as it approaches a point, or a rational function, which is a discontinuous function at the point x is equal to -1, but they're relatively simple. They're the same function throughout. Whatever values of x they are within their domain, they're the same function. Today we're going to look a little bit at what are called piecewise functions. A piecewise function is one that is a certain function with certain domain, and then when it's in a different domain, it's another function. We've already talked about one of these in grade 11, the absolute value function. The absolute value function, when, like for this one, which is the absolute value of x plus 1, when x, that works, when x is greater than or equal to 1, that's slightly different. When x is greater than or equal to 1, the function is x plus 1. Okay, so that's this blue line on the graph. So once x is larger than -1, we have that function x plus 1. When x is less than that, our function is negative x plus 1. And we would write that when x is less than, I should say -1 in both of those cases. So for this case, we look, what number are we looking at? Let's say it's -5. That's this top part of the function. So I'm going to use -5 plus 1 and then take the negative of it. So that would be our +4 up here. Piecewise functions are described like this. Different types of motion could be described with a piecewise function, etc. So what we want to look at when we have this piecewise function, and I touched briefly upon this in the lecture on Friday, was the idea of left-hand limits and right-hand limits. Now, in this case, the example, determine the limit of this function when x is greater or x is approaching 2 for our function h of x. So just using our graph, as x approaches 2, we can see that our graph is approaching 3. Now, it doesn't matter if I'm coming from the left-hand side, the negative side, or if I'm coming from the right-hand side, the positive side. They're both approaching the same number. And that means that the limit as x approaches 2 of h of x is equal to 3. Because both the left-hand side, limit as x approaches 2 from the negative side of h of x is equal to 3. And that is also equal to the limit as x approaches 2 from the positive side. They are both the same, therefore their limit is the same. Okay. Now, basically, this guy here is a problem. Does this have a limit? Well, in this case, it does, by the same reasoning I was just saying. But we do have to look when there's these points of sharp focus or points of discontinuity. We have to look at both the left-hand side and the right-hand side limits. So by notation, the limit as x approaches -1 from the negative side of our function, that is equal to 0. So we're looking at our function coming this direction. Hey, he's getting closer to 0. That's our limit. When we look at it from the positive side, so we're looking at our graph from the positive side, oh, it's also approaching 0. So the limit as it approaches from the positive side is equal to 0. Therefore, the limit as x approaches -1 is 0 because both the left-hand side limit and the right-hand side limit agree. Not all functions do that. We can also look at maybe something like this function here. If we were to look at this function from the left-hand side and the right-hand side as -1, we would find that this does exist in this case, but in some cases maybe they won't. Okay, this one does exist, we did that earlier. So here we have a function. We want to limit as x approaches 2 of this function. The function is defined as when x is less than 2, it's x squared. And when x is greater than or equal to 2, it's 8 minus x. So 2 squared, we're going to go to the left-hand side, and I'm going to use 2, 4, 6, 8. So x squared, when I plug in 2 for x squared, I would get 4, and then I would have a parabola to the left of that point. And then 8 minus x, I'm going to have a completed circle because it's greater than or equal to, and I would have a line going down like that. Well, it's not perfect, but I'll tweak it a little bit so it's a little shallower. Now, there is a sketch, it's not perfect by any stretch, sketch of our function. So let's evaluate our limit. As I'm approaching x, or as I'm approaching 2 from the negative side, my graph is getting closer and closer to 4. So my y value is getting closer and closer to 4. As I look at my graph and I approach it from the right-hand side, the right-hand limit, that's equal to 8. My y value starts getting closer and closer to 8. Therefore, since these two guys do not match, they do not equal to each other, this limit does not exist. A right-hand limit exists, a left-hand limit exists, but since they don't match, there is no limit for this function as we're approaching 2. We have one from the positive, approaching 2 from the positive, approaching 2 from the negative, but none approaching 2, or approaching 2 because the two do not match. Now let me just open up this applet. We can go through the work. So we got an interesting one here. You can see how the left-hand limit and the right-hand limits are working. Okay. So we can do limits in every place except 2. Okay. As I say, what is the limit of this function as x approaches 0? Somewhere around here, 17.5, 18, because the left-hand limit and the right-hand limit are the same. We cannot do it at -5. We cannot, or there is no limit at -5, and there is no limit at 4. There's a left-hand limit and there's a right-hand limit, but they do not match, so they are not equal to each other. So the limit as this function approaches -3 from the negative side, -3 from the negative side, looks like it's approaching 9. I look at that function again from the right-hand side, it also looks like it's approaching 9. Therefore, the limit as x approaches -3 is 9. When we look at our 4 from the negative side, so the left-hand limit. So we're approaching 4 from this side. Looks like it's approaching 2. Right, our function here approaching 2. So our left-hand limit is equal to 2. If I'm looking from this side, my y value as it's approaching from the from the positive side of 4, it's approaching -3. This function is discontinuous and it does not have a limit at 4. Because the left-hand and right-hand limits do not equal to each other. Okay? A function is said to be continuous at a point A if the limit of x is as x approaching A of the function is equal to f of A. Basically, f of A is defined at A. And I just gotta find my book. I kind of should have a notation there. Oh, f of A exists. That's the other thing. There is a number for f of A. So a function is said to be continuous at those points, or continuous if they exist. So for example, this one here is not continuous because there's a hole in the graph there, and it violates number 2. F of A, so f of 2 does not exist in this case. So this is not a continuous function. Okay, so it's not defined, but most often it's not. F of A doesn't, or f of A is not defined or does not exist in this function because there's a hole in the graph. This one here is also not continuous. We have a hole in the graph here. F of A does not exist at that point, and f of A does not exist at our vertical asymptote. Okay. This one is discontinuous. It's defined. F of A exists, so f at 0 exists, it's 2. So f at 0 does exist. However, the limit is not, the limit of f of x is not f of A. This one has no, or the limit of f of x does not exist in this case. So this is a discontinuous function, as all three of these are discontinuous for different reasons. Okay, so let's look at this. I'm going to go through quickly here. We have a nice function, no holes in the graph. Okay. Now, we have a couple, f at -4. So -4 here. As I approach -4 from the left-hand side, we are going to get close to infinity, positive infinity. As I approach -4 from the right-hand side, I'm getting down to negative, or I'm approaching negative infinity. Therefore, this function, limit of m of x as x approaches -4, there is no limit because those two guys do not exist. Or sorry, those two guys do not match each other. Okay, the left-hand limit exists, the right-hand limit exists. Since they do not equal to each other, the limit of x approaching -4 does not exist. This one, on the other hand, looking at m of x as we approach positive 1 from the negative side. So drawing the graph here, we can see that we are going to approach infinity. So this guy has a left-hand limit of infinity. If I look at the right-hand side, I'm also approaching infinity. So we have the left-hand limit and the right-hand limit do equal to each other. So the limit as m of x approaches 1 is infinity due to the fact they do exist. They do match each other. Now, this is a discontinuous function at this point because x at 1 is not defined. It's not within the domain of the function. Okay, if you have any questions, you may contact me on my cell phone today. And go ahead and use it in class or ask Ms. Lawrence. Not sure if she remembers too much calculus, but she did do it. So I will see you this afternoon.